This is a quick summary and an extension of what I talked about here for 25 minutes. You got the rotating strap, you got the omega versus T. Pretty much everybody got a pretty good graph of that. And that's for omega T's in degrees per second, T's in seconds. I'm not going to talk about all that. We pretty much understand that. And if you don't, you need to go back and check the original video. And then we have our theta of T versus T, the total number of rotations from the beginning. The graph is going to look like this. The total number of rotations from the beginning never goes down as we go through time. Okay, at any time you stop the video, there's been a certain number of rotations from the beginning, and the further along the video you go, that number increases. So by counting the rotations in every minute, you can easily get a graph like this. Okay, so we've seen and we saw in class that a triangle, I call these fundamental triangles, with a horizontal and a vertical leg and a hypotenuse that runs between 2 points on the curve, has a rise and a run, giving you a slope. The slope is a change in theta, because the rise is a change in the value of theta, the time, delta t. The run is a change in the time on the clock. And that gives us an average angular velocity. That average angular velocity is the approximate angular velocity at the midpoint of this interval. You have an angular velocity at the beginning, an angular velocity at the end. And the angular velocity, as you know from this curve, is decreasing, and just from your observations, you know it's decreasing. So if you're going to pick a point at which to say the angular velocity hits the average, you're going to do it at the midpoint of this interval. Now, we can calculate average angular velocity over smaller and smaller triangles. Although you wouldn't want to do that with your graph, you can imagine that you have a completely accurate graph. You don't want to do it with your graph because, when the triangle gets this big, you're going to have a whole lot of trouble estimating anything about the rise and the run. You're going to have tremendous errors. So, as these triangles get smaller and smaller, you get average angular velocity on tinier and tinier intervals, which approaches the instantaneous omega of t. And if you don't remember how that works, go back and review the whole idea of how we define derivatives as a limiting process. And when we do that, traditionally, we'll keep the beginning of the interval constant. We'll go over smaller and smaller and smaller intervals that start at this point. And we approach, in the limit, the instantaneous rate of change of theta with respect to t. The instantaneous average, the limiting value of average angular velocities that approach the instantaneous angular velocity. And that instantaneous velocity is indicated by a tangent line. It's the slope of a tangent line at that point. In the other video, I took a straight edge, drew the tangent line. If you don't understand how that's done, review. I'll go back to that video. Okay, we take 2 points on the tangent line. Think about our fundamental triangle between these 2 points. It's going to have a rise, it's going to have a run, and it's going to allow us to calculate an omega. And that omega should be the accurate. If we had an ideally accurate graph and did this with complete accuracy, we would get an accurate value of omega. Now, at this exact time. And we could compare that with the value of omega predicted by this curve. So what I drew here, but ended up needing to label too much stuff, so I'm going to do it in a bigger graph here. As I said, okay, if we do this, if we take the slope of the tangent line at this point, then that's going to give us a value of omega. Now we're going to have to convert between rotations per minute to degrees per second, but it'll give us a value of omega that we can put on this graph. So it's going to occur, 2 minutes is 120 seconds, it's going to occur either a little bit above or a little bit below this curve. I'm going to put it a little bit above the curve so that here's our omega from the tangent line. Now we also had a data point at 120 minutes. Now that data point might lie above or below the curve. It's not possible. It's going to lie on the ideal curve. So you shouldn't try to make your curve go right through every data point. It's not going to happen. Your data points have fluctuations. You're going to have to wobble your curve around to go through all the data points. Okay, so I'm going to say this is your omega from the observed data. Okay? And it's omega at the 120 seconds. I don't have room to write the 120 seconds in here. And then, of course, you have it would be nice if these projection lines were horizontal, but this thing in the middle here that's the omega from the curve. So you have three estimates of omega. And there's even another one that we can throw in here. We haven't talked about the omega that we got by doing this big fundamental triangle, the average velocity between 2 and 3 minutes, because it's the average velocity on the second minute, the third minute, I'm sorry, that runs from the 2 minute to the 3 minute mark. Okay, so that average angular velocity would be more appropriately placed at the middle of the 2 minute or the 1 minute interval between 2 and 3 minutes at 2.5 minutes. So that's why I've got the 150 seconds here. Let's make that yellow. And we've got some omega on the 150 minute interval from 2 minutes to 3 minutes. Okay, well, hopefully that's a little shorter than the other one. That one went 25 minutes, this one's just 8, it's a third the length, so hopefully you can get what you need. But remember, there's a longer video you can look at with more commentary, and it might be worth seeing.